Hello, and welcome to our fourth webinar for New Zealand Oracle User Group and Latin American Oracle User Group community. And this webinar is with Mr. Arup Nanda talking about how to performance tuning on rack. And good morning to everyone from New Zealand, good afternoon to everyone from Latin America, and good evening or good morning already to Mr. Arup. I will say thank you to him again because he is going to do this webinar from India. From him right now is 2:30 in the morning, and he is awake just for us. And I don't need to introduce basically Mr. Arup. He's a celebrity in the Oracle world, a fellow ACE director. And without saying more, let's go and start with Mr. Arup. I will give the control to him right now. Thank you so much, everyone.
Perfect. Thank you very much. All right. So today we'll be talking about performance tuning in real application clusters. So as Francisco mentioned, my name is Arup Nanda. I have been an Oracle DBA for the last 16 years, and I continue to be one. I've been working with Oracle Parallel Server since 1999, and then I switched over to RAC in about 2000 timeframe. And since then, I've been working with RAC. Why this particular session today? I hear sometimes questions like this. We are facing some performance problems in RAC. What should I do next? That's not a very trivial question. It's actually a very, very important question because you've got to have some kind of an action plan to understand what we do when you issue a performance problem in RAC. Next question is that sometimes I'm using, let's say, 100 Mbps internet connection between the two instances of Interconnect. Is that adequate or not? Because about 10 years ago, 1 Gbps was not very common, but about 5 years ago was very common. Today, we are hearing about 10 Gbps. We also talk about InfiniBand and all that. So how do I know the one I've chosen is adequate, is enough or not? Oracle says that I can use cheap computers in RAC and have the same performance. For example, I can have, instead of having a 32 CPU box, I can have 8 4 CPU boxes, which are pretty cheap, and then I can make them a RAC cluster, and it will be performed exactly the same way as a 32 CPU box performs. Is that true? How do I know? Well, of course, like anything else in life, it depends. It has to be dependent on a lot of things. Depends on what? Let's see what happens then. What we get today is that some real life advice. I have been working as a DBA for a long time in the RAC, so I will just talk about from my own experience. I have not worked for Oracle, so I'm not going to talk about what Oracle typically says in the marketing. We will dispel some myths. We'll understand what are some myths and fallacies, and make sure that we will understand which ones are facts and which ones are actually just common wrong knowledge. We will understand how to formulate a plan of attack, make sure that the performance problem comes in. You can go and prepare a plan of attack, and finally, we'll have a real life case study. So let's talk about our Maya RAC implementation experience on 10G RAC, not 9i. In Oracle 10G RAC was introduced in March 2004. At that time, we were running Itanium platform running HPUX. And the Oracle version was 10.1.0.2. We tried to implement that, and result, we failed. In December 2004, the patch kit 10.1.0.3 was introduced. So we attempted to apply the same happen to put the RAC cluster for that. Result, we failed again. In March 2005, the 10.1.0.4 patch kit came out. At that time, we attempted and we were successful. Why I'm telling you this is, this actually told us a lot of things about how RAC actually behaves and how it actually performs, and not about just what we read in the manuals. And today, I'll be talking a little bit about my experience, what we learned that period of time when things didn't actually go very well. Our challenges were technology. At that time, there was nobody around in the world to give us an idea about what we could be doing on or what could be going wrong with our implementation. There was nobody. We were the only one that time. Second was, I was building a team that time. So the team was going to support the infrastructure. So building the infrastructure and then also training it to take care of it is sometimes a difficult proposition. In today's session, we'll talk about what are the different things the challenges we faced, and how we resolve them, along with some way-to-pay examples. First is that, why rack performance? All the tooling concepts in single instance applies to rack as well. So I'm not going to talk about the regular tooling things. Rack has other complexities. There's more than one buffer cache. There's more than one cache. There's more than one library cache, more than one row cache, and so on. There's a component called Interconnect that connects between the two instances. It's the concept of pinging and global logic. We want to make sure that we identify the right problem and go after it, not just a problem. To understand what the different problem points could be, let's see a little architecture of rack. So this is a picture I drew because it sometimes helps me understand very clearly what are the different components of rack. So if you start with that, let's say start with the very basic. We have a server or a host called node. The node has an operating system, naturally. On that, we are running clusterware. And I'm assuming I'm using the Oracle clusterware, not a third-party like a service card or HSCMP or some cluster. I'm using pure Oracle clusterware. In that case, I also need to have a volume manager that goes to storage and that goes across to the common storage from both the nodes. And that volume manager is ASM. Then on the top of that, we run Oracle instance, which is a combination of a bunch of processes and one area and memory called buffer cache and CI pool and all that. Then we have a listener running on the top of that, which listens to requests coming in. We have service that is on a specific instance or not. Then we have a virtual IP address, which is nothing but listens to the request coming in until it passes them to the listener. And if the node is down, the virtual IP goes over to the other instance. As a result, if instance 1 is down, and that gives us no access node to the request that's coming in. It is connected through a switch. And in the middle, we have OCR, Oracle Cluster Repository, which records all the information about the cluster. And in the middle, we have a voting device, which is used in case one of the nodes stops communicating with the other node. And in that case, that is used to decide which node should be in the cluster and which one should be evicted out. One little complexity is introduced here as a result of this instance. Instance is a combination of processes and memory areas such as buffer cache. But now we don't have one buffer cache. Now we have multiple buffer caches. So in that case, the cache fusion process transfer the blocks from one instance to the other instance, and that process is not. But we also have to make sure that there's a proper locking mechanism that will coordinate the locking of the buffers across the two instances. So this is like a very simplified picture of our rack architecture, of a two-node rack architecture. Why is it important? It's important because these are the points where things could actually fail. For example, if you have a storage problem at the storage level, let's say EMC SAN level, that will manifest itself in a problem with the ASM on this instance. And if you have a interconnect switch problem, that will manifest itself in the cache fusion or the lock manager. So that's the one. That's why you have to be clear about what are the different points you have to look into and go deep into that, which might not happen on a single instance. Two caches in rack, what does it mean? It requires synchronization. The word is synchronization, not replication. That means when a change is blocked change in one instance, it doesn't appear in the other instance automatically. It appears when the other instance requests the block from this instance. And that block, in that case, is sent across a bridge. And that bridge is the interconnect. Let's start with a little quiz here. Well, I can't see you, so I'll not wait for your response. But here's a simple example. If I have a very fast interconnect, assume interconnect has, that is speed of thought. You think it appears over there. It's not simple. I know it's not possible, but let's assume that it's possible. In that case, can I have a multiple node rack of the same total number of CPUs as a single instance with multiple CPUs? Can I have that? For example, can I have a 8 CPU boxes will perform the same way as a 32 CPU single instance database server? True or false? The next one is let. Now if the cache user is not right, that means if one instance is updated something, instance number 2 wants it, it doesn't have to go to the disk to get it. It can get that directly from the other instance of cache. That's called cache, right cache user. So in that case, I have a very high speed interconnect with the speed of thought. In that case, can I do away with a very slow I/O system? Because that will be cheap. Remember, it always goes to the buffer cache. So why do I care about the disk? So is it true or false? Because I don't need to worry about the performance of the I/O subsystem. Well, this is probably important to understand here. In Oracle Corporation marketing material, they show true to both the cases. Oracle says that do not worry about the number of CPU in a single box. Just go and buy the number of cheap boxes, multiply them by multiple node rack cluster, and you'll have the same performance. And the same thing also says that on the number 2 as well, don't buy expensive sand, just buy cheap sand, but buy rack. And then you'll also make sure that you get the same performance. They both are probably selectively true. They're probably most likely false. So the question comes in, why are they false and what are the circumstances they will be true? To address that question, let's see what exactly is why it shouldn't be true and why it isn't false. The total time a buffer leaves from one side and goes over to the other side. Here is the different timing. First, we find the block in the cache. Then we identify the master of the buffer. Then we get the block in the interconnect. Then the actual transfer speed of the buffer comes into picture. That's the interconnect speed. Finally, the latency of the interconnect has to come into picture. Once the block is transferred to the remote instance, somebody has to receive the block, create the consistent image of the user. If you look at this, the first 3 are CPU bound activity. They happen in the CPU. Next happen in the interconnect itself. And the third happens in the CPU. So the total time is a sum of all these times. Bunch of them happen on CPU, and only a few or maybe 20% of the entire activity happens in the interconnect. So now, do you understand? Even though you have a high interconnect, a speed of thought, you're not influencing the first 3 or the last 2. They remain the same. So just because your interconnect has become quite fast and I have absolutely no resilience in the speed of thought, even then you really can't have the performance you desire because still are bound by the first 2, which is CPU, or the last 2, which is CPU again. That's why it is not true that a high-speed interconnect will compensate for low CPU power. And that's the mechanism from here. If you want to understand exactly what happens during the cache coherence, during the cache fusion process, it's a session I have set for next week, sometime next week. That's where I'm talking about exactly how cache fusion works, how to identify the master, what a master is, and all that. We'll be sure to tune into that one. But in the meantime, understand that the cache fusion requires all these different stages. Okay, let's go to the next one. It all boils down to a very simple thing. Block access cost. The more the blocks we have, the more the time it takes. Particularly in parallel query. Parallel query may run in 2 different instances with the parallel query coordinator running in only one instance. In that case, every block that is done by the slave process has to be transferred over to the parallel the more blocks in that case has to be transferred across, and the block access cost will go up significantly. Block management cost. In this case, the more blocks we have, the more time it takes to coordinate that. As a result, it takes more time. Particularly things like an implicit cache check, like sequence numbers and all that. In that case, sequence number has to be implicitly checked, even though you do not check for it. Then further, the interconnect cost, the latency and speed, it comes into picture. Just to give you an example of what latency and speed is, think of a highway system, a freeway highway system where there is no lights. People can go over extremely high speed. That's because you have a, let's say, 100 kilometer distance between the two points in a highway, and highway speed is 100 kilometers. Does it mean you will take exactly 1 hour to reach from point A to point B? No, why not? Because just because the speed limit is 100 kilometers per hour, you'll not go in that speed limit. You probably would slow down because somebody will be another car in front of you. There will be traffic congestion and all that. So it will be faster than that. That's why it will be less. That comes the speed part of it. But that's not the only thing though. Let's say you can actually, there's no traffic. You can go at 100 kilometers per hour. Can you still make it at 1 hour? No. Why not? Because just because you can go at 100 kilometers per hour in the freeway system, most freeway systems actually have an entry point and exit ramp. So to go to the entry point, that is not 100 kilometers per hour. You may take some time because there may be a lot of cars waiting to get into the freeway. As a result, just to get into the freeway itself, you will spend about 5 minutes. Similarly, if you exit, same thing might happen. Sometimes you may have to take some time to get off the exit. That per person, just to get on the freeway to start the journey, that's called latency. So the more data you transfer, the more time, because of the latency and the actual transfer rate is out. So in hard lessons, sometimes you will be supposed to say, somebody will tell you that my instance, that my database is not functioning, is harm. Don't wait whether they take the word for it. You have to understand if it is really harm or it is really, really slow. How do you confirm that? Check the $3 session for wait time. If it is 0, then it is waiting. It's not waiting, it's really, really harm. If it is not 0, it is increasing. Then it is not harm, it's simply slow. When it is actually harm, can you still conclude that it's harm? No, you can't. Because it could be possible that $3 session is not being updated at all. This is so slow. So what do? You can take a system set down on all the nodes, wait for more some time, take another system set down, and check the values there. If the value is unchanged, the system is truly harmed. In that case, you may have no other recourse but to shut down completely and reboot it. But if it's slow, then you'll probably take care of things like killing the appropriate distance and all that, and then going ahead with that one. We have multiple OS troubleshooting. So we have a variety of things to troubleshoot the OS. Top command and the glance command are probably the most important ones. And then to identify what is going on in an OS process, we have multiple utilities. They vary from system to system, operating system to operating system. For example, trust command, and the stress command is in the Linux, and trust command in trust command in the HP UX, and so on and so forth. Okay, now we said, how do we go to the action plan? All right, in that case, I suggest a very simple thing. Start with the AWR report. Start with the top 5 timed event. That's not going to give you everything, but it's going to give you a good idea. In this example, we have a timed event called GCCR grant 2A. If you look at this, DB file sequential rate, you understand what that means. Because that's a single instance thing, nothing to do with this. Same thing also DB file parallel rate, rate by other session. But the GCCR grant 2A has happened about 1.4 million times so far in this period for the AWR report period. That means it's something serious. We have to think about it. What could be the causing that, and how do you reduce that? But to do that, you have to understand what GCCR grant 2A means. And similarly, if you see other events, what those things mean. But today, let's understand what they really mean. What causes the event? Only then you can solve it. All right, let's move on. Next one. Let's understand how GCCR grant 2A really means. Let's say I have two different instances, instance 1 and instance 2. Some session wants to read some block from the disk to the buffer cache because it's not found. Does it mean it can go and grab it? No. It has to go and ask for the block ownership to be granted to it, or to get an exclusive right on the block by the lock manager. Remember, this is an exclusive right on the block, not on the specific row. That's not something the Oracle cache, Oracle rack is concerned about. It's concerned about a specific block only. Say I want to update employee of row number row for employee number 1. Then session number 1 gets set first. In that case, Oracle doesn't return its only row number 1 from the disk. It gets an entire block from the database into the buffer cache. To do that, and also at the same time, let's say session number 2 wants to update for employee number 2, which is also on the same block. But at that time, the block is already exclusive. The block has exclusive lock on the block by instance number 1. So session number 2 is not going to wait for that instance to own the exclusive right in the buffer. So that's the difference. Session number 1 has a row lock on row 1. Session number 2 has a row lock on row number 2, but the overall block has been exclusively locked by instance 1, only once. That's the difference between row lock and instance lock. If you want to learn more about row lock and instance lock and why they're different, again, please turn into my next week's presentation on Under the Hoods of Cache Fusion, where you understand exactly how these things work. Today, let's just consider today, which is the session is trying to update and get the lock on the specific buffer. To do that, it has to go and ask the master of the buffer. This master happens to be on instance 2. Who exactly asks it? It's an LMS process of this node, instance 1's node, asks the LMS process of instance 2 node, which is the master of this buffer. Hey, can I go ahead and get it from the disk because I don't happen to have it? So one possibility is that LMS will check, I'm the master, but there is nobody actually has that buffer yet, and nobody has. So you go ahead and get from the disk. So a simple message comes back. But when the session requests the block for the first time, it doesn't know what's going to happen. It's possible it will get the block from the other instance directly. It will get the right to get the block from the disk directly, or it's possible that it itself is the owner of the buffer, master of the buffer. In that case, it doesn't have to ask anybody. He just go and do it whatever he wants. In that case, it doesn't know all that. So, but it has to wait until that determination is made. And that wait event, when it's simply waiting, is called GC current block request. That's where it's waiting. That's why it is called a placeholder event. A placeholder event is something that it doesn't know what exactly is going to happen next. That's why it waits. It's called GC current block request. Okay, so in this case, LMS of instance 2 says, well, I don't worry about it. The block is yours. So you can get the block from the disk because nobody else has it. In that case, it simply waits to be granted the exclusive right on the buffer. Remember, nobody has the buffer anywhere. Instance 2 does not have the buffer. Therefore, it can't give anything from its own buffer cache. It tells instance 1 that I'm the master. But you can go ahead and get from the disk. At that time, it has to wait for something. That wait on session now it changes to GC current grant to wait. Why grant to wait? Because it has to wait for the grant to come from the other instance. And when the grant comes, then it goes and reads from the database side directly. At that time, it waits for the other common wait event, which is DB file sequential read or a standard read at that time. But until the grant is given to it, it's going to wait for GC current grant to wait. So now you might be wondering, well, first time I started waiting for GC current block request. That's a placeholder event. Good, I got that part. So that is very quick because right away, this is a very short way. So it will know right away what course of action it's going to take. Next is going to wait for the grant to come in. Okay, why should it take so much for the grant to come in? If you look at this in the picture here, one thing should be very clear to you. There is only one way to communicate between the instances, and that is between LMS processes. LMS is a process after all. If the process is extremely overcrowded with requests, naturally your request will be slow because your time will come in the queue the much longer period. As a result, you will be waiting all the time on the GC current grant to event until LMS gets a chance to go to the request, send it across to other LMS. Other LMS will also get a chance to work on the request and send the response back that, yeah, nobody has the block, go ahead and act on the disk. And that doesn't come to the LMS right away if there's a lot of processes waiting for the chance in the CPU. And this is exactly what happens if LMS has CPU starvation. We'll see that. And all the time, the session on instance 1 is going to wait for GC current grant to wait. Okay. All right. Let's go to the next one. A slightly different scenario. Remember I told you in this first case, instance 2 does not have the buffer, all right, which is good. What if it does have the buffer? In that case, instance LMS goes to instance thing, LMS goes to LMS to instance 2. At that time, session is going to wait for the placeholder event called GC current block request. At that time, LMS says, hold on, I'm the master, I know that, but I have the block in my buffer cache. So don't go and get from this desk. At that time, it's a complication. The buffer does exist in the buffer cache, but it has some uncommitted transaction changes which have been flushed to the log buffer yet. Think about it. How many times the log buffer gets flushed from the log buffer to the actual online log files, ORL, the online log files? Is it continuously? No. It happens at multiple times. One, it may happen at every 3 seconds. It may happen when the log buffer is 1 MB full, or is on third full, or a commit happens. So it is possible that the log buffer has not yet been written to the disk, not written to the online read log files, ORLs. So what's going to happen if that is the case? That means the buffer cache, which has some uncommitted changes, not written to the ORL yet. If the cache fusion process picks up that dirty buffer, sends it across the interconnect to the other instance which is requesting it, what will happen is, suppose at that time, instance 2 crashes. At that time, instance 1 has to go and recover that buffer. When it recovers the buffer, it will go check into the online log file whether it has been committed or not committed. It will find it's not committed. But how does it know what changes were supposed to be there, which are supposed to be applied to the buffer in the disk or to be rolled back? It doesn't know that. It is committed at the time. So it must be rolled forward in the disk because it's committed transaction. But that is not found in ORL, the online log file. As a result, the instance recovery on instance 1 will not know what changes to roll forward to. It will lose all the changes. Therefore, LMS cannot just go and grab the buffer from the buffer cache and send across to the other instance. It must make sure those uncommitted transaction buffers in the log buffer are written into online redo log files before sending the buffer from the buffer cache over to the other instance. What it does, it sends a message or posts a message to log writer. The log writer then goes and flushes the log buffer into redo log files, and only then it sends the block across to the other instance. Until the log buffer is completely flushed, it's going to wait for log file sync wait event on the instance 2. And all this time, and then only after that, the log buffer goes to, and the buffer from the buffer cache goes into LMS, goes into the LMS other instance, and it goes into the session. all this time, the session which has requested the block is waiting on a different wait event. It's called GC current block to wait. Remember the previous one was GC current grant to wait. Grant to wait simply said, hey, give me the grant to lock the buffer in exclusive mode. Once I lock it, I'm done. I don't have to lock it again. But in this case, second case, I don't want a grant only because I can't get from the desk. You have to give me the actual block itself along with the grant. In that case, he's going to wait for GC current block to wait. Block to means I'm waiting for actual block to come in. In grant to means I just want a grant to come in, and then I will go and grab from the desk. So these two you have to understand very carefully because these two are typical wait events. So what does it tell you? What if the I/O is slow in this case? If I/O is slow, the log buffer will not be flushed immediately to the online log files. As a result, it will be slow, and the instance on instance 2 will wait for log file sync. All the time, in session on instance 1 will be waiting GC current block to wait without realizing what is going on there. So whoever told that the slow I/O subsystem is okay, particularly in the write cache fusion, not true. As you can see, I/O significantly impacts your performance, and particularly GC current block to wait. Same thing also goes here. If LNS is extremely crowded, it's serving for the CPU, or there's a lot of processes in its own queue, it's going to be slow in responding to the request for instance 1, and the session is going to wait for that as well. And also, in this case, the actual block get transferred from instance 1 to instance 2 as opposed to a single message saying the grant has been made. That's the big difference. If an actual block is transferred, the block transfer state, the latency, and all that also come into picture. And that will drive up the possibility of a GC current block two-way. Okay, now if since it is two-way, has to be a three-way. Let's see how the three-way occurs. The only difference is exactly similar. The only difference is instance 1 is the requester, is requesting it just like you were. Instance 2 is the master with a little twist. The master says, well, I don't have the block. I know who has the block, and that is instance number 3. So go and grab from instance number 3. In that case, it's going to wait for GC current block 3-way. So this identical situation, I don't have the block, instance 1, I don't have the block, but I can't just go and grab from the disk because I have to go and grab from the other instances of cache. But which other instances of cache? I have to go and ask the master. If the master has the block itself, then I'm going to wait for GC current block 2-way. If the master doesn't have the block, but somebody else has the block, then I'll wait for GC current block 3-way. Now, can you tell me, will there be a GC current block 4-way? No, it can be, because the combination of requester, master, and holder are only up to 3 instances. So if you have a 3-node rack or a 25-node rack, it doesn't matter. You will always have only 3 hops of the request. Requester goes to the master to understand who has the block, and then the holder then goes to the holder and requests the block. That's it, 3 at a time. There is no 3-way. Also, same way, can you tell me why is this possible to have a GC current grant 3-way? No, there will be no grant 3-way. For very same reason. The grant is requested of the master, and there is only one master of a specific buffer, and that's it. The request has to come from the master. The time it is to wait. There is something called 3-way. There are not 2 different masters of the same buffer. Only one. So there is nothing called 3-way. If you want to learn more about masters and how the masters is decided, how the locking actually made, and all that, again, I'll be talking about that under the hood of cache fusion, GES, GRD, and PCS. Now that you understand the most common wait events, and those are the most common wait events, 90% of the wait events you will see in RAG are those. And now you understand how to resolve them. Let's go to the next one. So in this statistics again comes in. Here is has received 293 blocks via cache fusion, and it has sent 271 blocks. via case fusion to other instances. If you compare this with all the other instances, the AWS port of other instances, you can see that we may see that one instance is sending out a lot more compared to other instances. What does that mean? That means that in that instance has a lot of blocks which other instances are requesting. Then you might want to drill down on that and find out why that is the case. Why would an instance have all the blocks which other instances want? Because by probability theory, it should be randomly spread across all the instances of the cluster. So there must be something wrong with the way application is designed. Well, that's about blocks. What the grants you mentioned. The grants actually come through messages. That comes to the next one, GCS hyphen /GS messages received and sent. Those are the messages that for requesting a lot of things, including grants. That also can also specify here why there are a lot of sessions requesting grants from this instance. So there's something that this instance is mastered a whole lot of blocks. So how can I address that? We'll see that here. Let's go to other block events. We have another event called GC current CR block lost. When the blocks are lost due to interconnect of the CPU, and you are waiting, you can see this message called GC current or CR block lost. GC current CR block busy when the read request was simply delayed. Most likely an IO bottleneck. When you see in that case, because this request was delayed and the next one was congested. That means it has not come in yet, but the requesting instance is simply waiting for that to come in over here. And generally that happens if you in case of a memory deficiency. And in a memory deficiency, the CPU is so much overloaded that the long queue is so high and the CPU is overloaded. By the time a process gets a chance to run on the CPU, it has no memory to phase out its stuff to. The phase goes into swap, and when it does, the process goes into the CPU run queue. At the time, it can just go and get from memory very quickly. You have to wait to be swapped into memory. That is the problem sometimes. Okay, let's go to start the first one. Interconnect issues. Before that, let's do one more thing. Buffer busy events. What causes the buffer busy events? This is one. Want to bring something to the buffer cache. There's a delay, however. Why? Because space is not available on the buffer cache. It has to go and phase out some of the buffers from the buffer cache to make room for the new one. Possibility number two, delay because the source buffer is not ready yet. Number three, the I/O is extremely slow. As a result, the delay in pushing the buffer out. Or finally, the redo log is being flushed. That we saw why that is the case before. The redo log has to be flushed so that the uncommitted transactions in the buffer cache in the buffer can now be transferred across into interconnect to the other side. This is something doesn't happen in a single instance. This is something happens only on rack. In summary, a log buffer flush could lead to GC buffer busy wait events. You might think they're disconnected events. Now you see why they're connected. And this is one of the reasons why we highly recommend that if you have a choice in designing up storage, and sometimes you may not have because you may have to have a cheap storage or cheaper storage, but invest the most expensive and fastest possible SAN for the redo logs. And this is exactly why, because the I/O on the redo logs are the most likely to impact the rack performance, not the database vector itself. And it's possible the redo logs are very small, so you don't have to invest a lot of money on those redo logs only. We moved from a regular EMC SAN to solid state devices for the online log files only, but the impact was amazing. The performances went up by almost 6 times just by doing that. So you can do that intelligent analysis a little bit and then find out if that's going to help your performance. Parallel query. One big issue in rack is the parallel query that goes across many nodes. For example, a query coordinator may run on instance 1, and the two slaves could run on instance 1, 2 other slaves could run on instance 2. And the blocks together, they're sent across the interconnect to the query coordinator. And that's where the problem lies. The query coordinator waits for the blocks to arrive from other instances via the interconnect, and then slows down the processing. And those blocks which runs across the interconnect, they also slow down the processing and everything else. So how do you do that? Is it possible to restrict a parallel queries to a specific node only? Yes, you can. And that you can do by something called two parameters in init.ora called instance underscore groups and parallel instance group. Let's see this one. In this, if you have defined parallel instance group PQ group 1, suppose, when a parallel query runs on that instance, Oracle is going to look for which instances have instance groups equal to PQ group 1. In that case, it's going to find only the instance 1, that is ProDB1, has an instance group defined as PQ group 1. Therefore, all the parallel query slips will run in that instance only. It will not go to any other instance. Similarly, you just connect it to ProDB2. At that time, the parallel instance group is PQ group 2, and then it will find out which instance has PQ instance group equal to PQ group 2. Again, it will find ProDB2 as instance 2 is the only one, and it will run the PQs only on that instance, not go to the other instances. These are important parameters. Instance group parameter is a static parameter. Parallel instance group is not static; it's dynamic. You can do alter session. What about you really want to go across multiple instances as a DB or something? Can you do that? Certainly. But in that case, we define two different instance groups. So you can say instance groups to PQ group 1, comma, PQ 2 nodes. And on instance 2 in Aurora, you put PQ group 2 and PQ 2 nodes at a time. And then you can do alter session set parallel instance group equal to PQ 2 nodes. When you do that and run a parallel query, it's going to check which instances has been defined as an instance group to PQ 2 nodes. It will find that instance 1 and 2 both are great. It's going to run the query on both the sides. That's what it means by the parallel. That's what the function of parallel instance group is. Okay, let's just go to. I'll just go to the case study because that's a lack of time. It's very important. And let's have a look at the case study. Here is the actual case study I had. Remember, this is a snapshot from the grid control performance page. This is a snapshot after the problem was resolved. That's why we saw something going up, and then this coming down after that. When the problem actually happened, obviously it wasn't going down that time, it was going up and up. So I had to go and find out the reason for that. This is a great example of the case study. Okay, when I saw that first time I was going up, two specific events popped out right away. They're increasing. That's in the green color, in light green, little teal green color on the bottom. That is GCCR failure, and the light green on the top. That is GC buffer busy. Those two were significantly high events and going up and up. And by the way, I don't have to guess for the color. Right below that also shows you the top time event, and then they're right there. GC buffer busy and GCCR failure are pretty high. They're increasing significantly there. I have to understand why they're increasing. So remember, from our previous explanation, we understood when the GC event occur. The first thing that may come to mind is, well, global cache. It is not getting global cache, that means the buffers, from the other instance. Makes sense? What is the first thing that pops into your mind when you think of buffers are not arriving from the other instance or they're failing? The first thing, of course, comes into mind is network. And that's the first thing. So we should do the first one, the network. ifconfig -a shows network traffic. And what we should do, we should look for anything congested, dropped, or collided. It shows very clearly there is no congestion or no drop packets. That's the problem then. If there are no drop packets or no congestion, why are we saying lost packets? GCCR lost packets. Think about from the earlier explanation. A lost packet is not, the packet is being transferred from one instance to the other instance on the buffer. It's not just the interconnect network itself, it's other things as well. For example, somebody has to prepare the buffer to be transmitted. then it's transmitted. And then somebody has to receive the block from the transmission unit and then prepare it to be given to the end user. This prepare it before and prepare it after receiving, that's a function that happens on CPU. So just because the network is, it may sound like the buffer is not getting transferred, it doesn't mean the network is a problem. In fact, if you go to ifconfig-a, the network actually, its form is not the problem. So we had now at this time, we have to worry about what else is the cause. Well, very simple. CPU. CPU could be the cause. But let's see the CPU time, top command. We saw the top command shows 1% idle time node 2. But wait, 1% idle time. That's a node 2. The problem we are seeing right now is a node 1. And node 1 has about 40% idle time. That's a lot. So node 1 is a 40% idle time, node 2 has 1%, but the problem we are seeing right now on node 1. So why could there be a problem then? CPU is clearly, CPU is not the problem here. On node 2, which is 1% idle time, we saw two processes, LMS and LMD as the top processes. I know you have a bunch of net backup processes which are on, and they also consume CPU. And that's a problem then. We have to do some further analysis. Let's see, this is something we do on instance 1, which is node 1. That's what the problem is. Select stuff from instance gas transfer when I passed for the data block. And we got this value. Look at the value, current congested. That's a pretty big value. But remember, this is a $3 view. So it doesn't mean anything. It is since it's time the instance started. So this number itself doesn't mean anything. Maybe it's already there, something we had a problem or something. It's not necessarily an indication of problem right now. So what we have to do, we have to wait for some time and then run the query one more time and look at the value. Is the value increasing? You can see that it actually is increasing. So the current congested value is increasing all the time. What that means is the instance is waiting for a lot of congested blocks. And we also saw that. We confirmed that from the wait event, GCCR failure as well in this process. Why could that be congested? Think about it. A congestion typically happens if it is a long run queue and or a CPU starvation. But hold on a second. It is CPU starvation. We know on node 1 there is no CPU starvation. There is CPU starvation, however, on node 2. And node 2 CPU starvation means LMS and LMD are not getting enough CPU to process the request that comes from node 1. As a result, node 1 simply stops responding to the request and the performance comes down. So what we did at the time diagnosis was a CPU starvation by LMS and LMD processes are causing GC wait events. What is the solution? We understand we can't kill LMS and LMD, of course, because those are key processes. But the net back processes we killed. Once we killed the net backup processes, the CPU consumed by those processes were giving to LMS and LMD immediately. And they could process all the requests. And the problem immediately vanished. It took some time to come down. That's why using the picture you saw it is going up and gradually came down. But after that it was completely down and everything was back to normal. Go to the moral of the story. The moral of the story is if you see a performance problem on node 1, and you see no CPU contention, no IO problem, anything on node 1, it doesn't mean the problem is only on node 1. If the problem is on node 2, it will also affect the performance of node 1. So in a rack cluster, problem on a specific instance might cause a problem across the entire cluster. That's something you have to carefully understand and know. So it's because you saw no problem on node 1, it doesn't mean that the problem was in node 1 itself. The problem was in node 2. And in this case, LMS and LMD were clearly the problem. And they could not find the buffer. They couldn't process the request from node 1, so node 1 had to wait. And by removing the problem on the other two nodes, you just remove the problem. This is something I want to stress extremely highly, because sometimes I've seen a lot of people running rack cluster when they dedicate one node to a batch process, for example. and they dedicate the other nodes for OLTP. And the reason they give is that, well, let that batch processing node get overloaded and be hammered with IO problems, LMS problems, CPU problems. Only that node will be affected because batch processing is something we do not care about for performance. It might run a little bit slow, but at the end of the day, it will complete. We care about the performance for OLTP applications, and therefore we remove the OLTP and move across to other instances. Now, after what we learned, do you think that is true? It's not. If a batch processing node is slow, if the batch processing node has CPU and memory or IO problem, it is going to be slow in responding to other instances requests. And the other instances will also slow down as a result of that. So it is not a good idea in general to separate the batch processing and OLTP across multiple nodes and then think the batch processing or problems will be limited to that node only and not be visible across all the instances. Okay. So now what's the first one? Another questions we had answered. That how much of the interconnect should be good enough? Actually, as you saw, the interconnect plays a very little role in the overall chaos fusion process. The CPU plays a much more important role. So you should have a high throughput interconnect, but it doesn't have to be extremely high. We just saw that reason why. But it has to be low latency. If it is more latency, it takes more time to be on the queue and to be sent across. It has to be reliable, of course, because if it is not reliable, it will drop the packets, and then chaos fusion will solve at that time. So what you can do is simple things you can do. You can use a simple 1 gig Ethernet or 10 gig Ethernet, and then but the interconnect must be on a private LAN. If you have multiple network ports, you should do some kind of port aggregation to increase the throughput. For example, APA on HPUX, multi-NIC on Linux, and so on and so forth. But most important, the third one, if you're using gigabit over Ethernet, you should use something called jumbo frames. Why jumbo frames? Think of this. Every packet that gets transferred across from to the interconnect by the network is actually by default broken into something called the transfer units. And the transfer units are like chunks of data coming from instance 1 to instance 2 all the time. And that unit is typically 1500 bytes. But if your typical data block size is 8 kilobytes, then you need 4 of the chunks to get from instance 1 to instance 2. What will happen is that when the chunks are sent across, they're not sent in the same order or by next to each other. They may be sent in any order. So somebody on the receiving side has to get all these chunks and reassemble the block. It takes time, also increases the error rate. What if you increase that chunk size to 9,000 bytes? In that case, instead of being sent in 4 different chunks, it will be possible to put them into a single chunk. And that's called a jumbo frames. Alright, so how do you check the interconnect is being used? Very simple. OIF, CFC, get IF, that shows you the interconnect used, in this case LAN 902. So you have to ask your sysadmin, if LAN 902 is bonded, that means it's a high-speed interconnect, also is it bonded by 2 different ports together? If not, you can use OIF CNG set IF command to set a new LAN port for the interconnect. That's a very simple thing to do using OIF CMG set IF command. Okay, in summary, planning, you have to have adequate CPU, very simple, and network and memory. You have to plan all for sequences, if gas and no order. The table spaces read only. Again, I couldn't cover all that with a lack of time, but if you download the presentation, you can understand what I mean by read only table spaces and how they do it, and compact small blocks, and so on and so forth. Diagnosis. How do you use diagnosis? I always start with the AWO report. That's not the best way to start all the time, but that's certainly the best way in many cases. So you start the AWO report. Identify the symptoms, and most important, understand why. Now that you understand the symptoms, DC current block 2A, clan 2A, block 3A, and DC current block request, and so on. Now you understand why they happen. So now you understand, just because the word DC happens there, it means that a network or interconnect issue. That is not true. Now you saw that could be a problem with the CPU itself. It's not just network problem. Then you find the correlation between the drop packets in the network and the CPU usage from SAR and GC buffer loss in AWR or system reports. If you see that there have been drop packets in the network, that means obviously it's a network problem. But then that is not the only reason though. So if the network looks okay, you go back to CPU usage with the SAR and find out was the CPU extremely overloaded during that time. If it was, then you go, that's the cause. So when you say GC buffer lost in a AWR report, you will be able to correlate that. Now the next question is that if the CPU is overloaded, why is it overloaded? LMS element is not really causing it overloaded, it's a victim of the problem. So in that case, you have to find out what is causing it. Let's say somebody is running a compression utility. Let's say somebody is running an encryption utility or something. Or just like in the previous example, somebody is running a net backup process and a bunch of them, and that was the problem. So you have to find out the reason why LMS is not getting enough CPU to do its job properly. With that, I thank you very much, and I open up for questions.
Arup, hi, how are you? This is Francisco. Can you hear me?
Yes, I can.
Hi, Arup. At the moment, we have 3 questions. The first one was regarding your case study you present. Can you have done an AWR on Node 2 for the same slice time?
Okay, great. So why didn't I do an AWR on Node 2 on the same time slice? Great question. But actually I did. But in the AWR on the Node 2, I actually did not see a problem. Why? Because Node 2 was not experiencing the problem. Node 2's LMS could not satisfy the request coming from Node 1 LMS. That's why all the sessions of instance 1 were waiting for that problem. Whereas in instance 2, nobody was requesting anything from instance 1. Therefore, I didn't see a problem. So if I had seen a problem on Node 1 and Node 2 at the same time as well, that would not have indicated the root of the problem. To find the root of the problem, I have to go across to understand what would have caused it. Let's say I saw the GCCR block failure or GC current block failure. So from there, I have to understand the cause. What are the causes? Cause number 1, network problem. Cause number 2, CPU congestion. So that's, I immediately went to network first and identified network. I ruled out that is not the case. Then I had to jump to the next conclusion. CPU problem. Then I have to see the CPU problem on Node 1. Hey, CPU was actually okay. Then only CPU problem in Node 2. Hey, it's not okay, and that caused it. So this is the key message here. I should not stop at the problem diagnosis at the node where the problem is happening right now. I have to expand my diagnosis across all the nodes of the cluster.
Thank you, Arup. And basically, if anyone wants to do a question, you can use your chat option in the right side of your screen. And the next question I have is how many LMS processes we can have at a time?
Good question. So first of all, remember, the job of LMS is to transmit goods back and forth. So you might immediately think, hey, if I have more than one LMS, the problem is solved. In that case, one LMS will not be able to handle the request, 2 LMS will be better, and maybe 200 will be even much better. But think about it. If LMS runs, and LMS also processes like any other process, each process gets a slice from the CPU processing. So they get a slice, they run the stuff on CPU, then they have to move on because other things have to come in. If you have a if you have a single CPU box and you have LMS process, LMS gets a time slice. Let's say you run 2 LMS processes on a single CPU box. What will happen? They will not run at the same time. Again, the CPU will give them some time to LMS1. After that time slice is over, it will throw away LMS1 from its own run queue and get LMS2 is run queue. LMS2 will run for some time and they will be thrown out and to go back to LMS1 and so forth. As you can see here, you didn't help the problem. You actually made it worse. Because now, each LMS will have to manage its own process where it left off and all that thing. So you didn't actually solve the problem. So LMS process can go up a lot, but making it more than half the number of CPUs in the system is completely useless. It could be actually detrimental. You can, however, experiment by increasing the GCS process, number of element processes, and you do that by using GC servers on the GCS servers on in the init order parameter. You set to a value. Typically, you start with half the number of CPUs you have, and if you see that, will give you a little bit of advantage. But increasing anything more than the number of CPUs itself, you actually will make the performance the worst possible.
Thank you, Arup. Suppose we have a six node rack. If we see GC CR current block request on node 1, to troubleshoot, do we only need to go talk in diagnosis of only master node or request? To troubleshoot, we only need to go to in diagnosis of only master node, request, and holder? I don't know if you understood the question.
Great. Yeah, I understood the question. So let me repeat, if I understand the question correctly. So if I have a 6-node cluster, and I see on, let's say, instance 1, I see a lot of wait events with a GC current grant 2A. And grant 2A simply means instance 1 is requesting the grant to be given from the master to itself. The master or the holder, they don't have the block themselves. So in that case, how will I find out who the master is and how do I go and diagnose the master level? Actually, that's a little bit broad topic. So I am actually going to cover that in detail, what the master is, how you identify the master, and how you go after the master and get it, but under the hoods of Cache Fusion. That's going to happen next week. So instead of describing here, I'm sorry, I won't have the time to describe it completely and make a good job at it. I'll ask you to tune into that under the hood of Cache Fusion. That's webinar next week, and learn for yourself how you can do that diagnosis yourself very clearly. You understand.
Thank you, Arup. The last question I have is, at the beginning, at the beginning you talked about cheap hardware. Do you recommend the use of Intel to do rack?
Great. So that's I have to answer the question very carefully. So first, let me say, if I understand correctly. So if I have cheap hardware and I'm putting rack here, should I from the topic, from the discussion we had before, you might have seen very clearly that it depends on a lot of factors what get transferred. So you saw the GC current and 2A. This happens because the requesting instance, that is instance 1, is not the master. Instance 2 is the master. That's why it has to go and ask for the request all the time. And that's why it has to consume CPU cycles. What if the master was still instance 1? In that case, it doesn't have to go and ask it. And that wait event will no longer apply. So, if you design your application in such a way, the holder, the master, and the requester are in the same instance, you will never have to go and request either a block or a grant from another instance. So you will never see those GC wait events. In that case, you can certainly go for the cheap hardware. So there's absolutely no reason why the hardware should not be a problem. It should be a problem at that time. You have no CPU contention, you have no block to be transferred across all the interconnect, and so on and so forth, so no problem. But a typical application is probably difficult to do that. You probably spread across all the instances of that. In that case, the blocks will have to transfer across back and forth. A block will be requested on the other side, which is not found in the local cache, and so on and so forth. In that case, if the hardware is not enough, it doesn't have enough capacity, it's going to slow down your entire processing. So Intel, in the same way, Intel or nothing, it doesn't matter. Can you do rack on Intel? Of course it can. But think about it. In this case, that's not the same thing as, let's say, simple example. You have Intel Core 2 Duo. If you have a two CPU Core 2 Duo chips, that means overall of 4 cores in the box, that is not the same as two core machines. Because that way, you are paying a lot of penalty for this interconnect transfer back and forth. So you have to think about that now. So don't just multiply the number of ports you have and make it the same in the single instance. It's not. You have to pay for the penalty.
Okay, Arup, I have one more that just popped up. You mentioned that separating batch processes from OLTP processing is not recommended on two-node rack. Why would there be a GC wait event if sessions are directed to specific nodes?
Okay, good. So let's see the first one. If you run a batch process on instance 2, say a two-node rack, I run a batch process on instance 2. What does it mean? Batch process simply means there are updates happening to specific blocks of the table. And on the OLTP node, which is instance 1, you are either selecting, updating, or doing something to those blocks. When you run a batch process, they gather a lot of blocks of the table and they store in the buffer cache of the batch processing instance. When the OLTP instance has to do something with those blocks, it has to go and grab the blocks from the batch processing node all the time. Then once the blocks come over to this side, then that gets something called exclusive current, right, on the block, on the OLTP node. But the batch processing node is not done yet. It is still processing it. So it has to go and grab it, the block one more time from the OLTP node. Now see a problem? You are forcing this back and forth just because you are separating it. If you hadn't done that, let's say you are spread across all the nodes, which is the batch processing was running on both the nodes and OLTP was running on both the nodes. In that case, it is possible that the block being requested by the batch process and OLTP process, they have the same instance. So there is no need to go to other instance to go and grab it. But by separating, you are forcing this block transfer a lot. So either way, the block transfer has to happen. There's no preventing it. But if you separate it out to, if you spread across all the nodes, the possibility that the block will be found in the buffer cache locally is actually much more compared to if you had done it separately, block and one OLTP and one for batch processing only.
Okay, Arup, one more, sorry. Do you have any benchmark for the interconnect traffic performance when using public switch, private switch, and private switch with jumbo frames?
No, I don't have a benchmark performance, but that will be very difficult to specify. That will depend extremely on your specific environment. So it's difficult to do a benchmark. I believe Oracle has done some benchmark with the Oracle e-business suite. That's a very common standard application. That is probably found in OTN. I don't have it right now in front of me. I don't have access to it either. But you can probably look for that. But again, that will be very generic. That's not going to help you. So you have to understand that in your side, how much is going to help you. And you can do that by doing these things. There is, if you look at VLAN systat, the systat has all the GC related statistics. So you have to find out how much you are doing. Actually, you don't have to do that. You can just go to AWR and get everything from AWR itself. And that would tell you very clearly how things are moving from one instance to the other instance. And in terms of who's going to help or not. But without that, there is no specific benchmark. I have run some tests on my own applications, and I've seen performance jumping up to about 6 times simply by implementing jumbo frames. And you know why? Because to transfer a specific block, 8K block, you require now exactly 1 packet if you have jumbo frames. If you didn't have jumbo frames, you have to they now require 4 different chunks. Because it's a 1500 bytes is the typical size of the MTU. So now 4 different chunks. Now the question is, does the time increase by 4-fold? No, not necessarily. Those chunks are there are 4 different chunks for a specific block, but they're not sent in sequential order. They're just sent across as the time comes and then sent across the side. On the other side, they have to reassemble it. Imagine if there is little traffic in the interconnect, a reassembly won't be a problem. It will be very, very quick. But if there is a lot of traffic flowing across the interconnect, that reassembly will take a long time. As a result, your performance will be worse. That's what I'm saying. It's very important to understand is in your own environment. There is no specific generic answer. So for your own environment, the cascading traffic is pretty high. Jumbo frames will help immensely. But your own environment, The gas fusion traffic is low, then jumbo frames won't be as dramatic as let's say high traffic. So you have to see that in the whole environment. In one of my cases, I'll tell you, I saw a 6-fold increase in performance just by implementing jumbo frame because there are high data transfer between the lenses.
Okay, Arup, the last part of his question that I just saw, on my rack setup, we are using public switches. Sorry, on my rack setup, we are using public switches. How much is impacting my performance?
A lot. So, first of all, you are using public switches for what? You are switching for public interfaces like the VIP, or are you using for private cluster interconnect? So if you're using the switch for that, imagine what is the problem if you have a switch? A switch is like a highway system, suppose. In a highway system, what if you are the only driver on the highway? In that case, you don't have to worry about any other driver. You can just go and run anything you want and you'll be very fast. But that's not possible. The typical problem is in a typical highway system, you have other drivers and other cars in the system. So you might collide with somebody else if you don't watch out carefully. And that's exactly what happens in a private interconnect. In a private interconnect, a lot of traffic passes back and forth between the two nodes. If you put that on the public switch, the switch doesn't know what is what. So it doesn't provide a collision-free environment for that traffic. It mixes that with the public interface as well. There will be collision, as a result you have slowdown. So best option to buy a switch, separate switch for the interconnect alone. That's the best option. What may not be the possible option because of the cost involved in that. So what is the next best option? You can still use the public switch, but create something called a private VLAN for the interconnect only. When that happens, it's like you have a 3-lane highway. One single lane is dedicated to yourself and nobody else. So you're still using the public switch, public network and everything else, but a specific part of the highway system, that is one lane, in this case the private LAN, that's all yours. So you're not going to collide with anybody else there. So how much it is costing you, it's very difficult to say that because again it depends on how much traffic goes back and forth and how much collisions you see. But it's always good to just to not worrying about how much you are paying for that, but simply create a VLAN. That is not difficult, that is very, very simple, and the VLAN will save you a lot in performance.
All right, Arup. Thank you so much for your time. Thanks so much for coming and for all the sacrifice to be awake very early in the morning in India. And I just hope to have you for the next webcast. And what else I can say? Thank you so much for the great presentation you did today.
Thank you very much for inviting me, Francisco. So I just want to make sure that the next week's presentation, Under the Hood of Gas Fusion, actually that's what I've been the first one. So I asked all the participants today to attend that one to understand how the gas fusion really works and the locks actually happen, why the locks are required, and how the lock upgrade and downgrade happens in this case. For example, we talked about the grant event. Grant event is something we are asking the other instance to give us the grant to the lock. What kind of grant is that? What kind of lock is that? That's something we will discuss and cover with a demonstration in next week's presentation. So I will urge everybody to join that if you can. Thank you once again for inviting me.
Thank you, Arup. See you next week. Thank you, everybody, and see everyone next week too. Bye-bye.